Hello everyone and welcome back to ASFC Chemistry. In this video I'm going to take you through Born Haber cycles. I'm not going to be looking at any of the enthalpy of solution Born Haber cycles in this video, but what I will do is be looking at the examples where you use a group 6 non-metal, so that's going to be something like O2- or S2-, and I'm also going to look at examples where you need to do multiples of any enthalpy change values in your calculations. So I'm going to use 2 different cycles to do all of this. Let's get started. So this first one is for KBr, so that's just potassium bromide, and you can see here I'm putting it in the solid state on the bottom line. State symbols are really important throughout these. Now this first enthalpy change, represented by the downwards arrow, is an enthalpy change of formation, and the downwards arrow tells me that this is an exothermic enthalpy change. Now for the KBr, for an enthalpy of formation, I need to make sure I only make 1 mole of the KBr shown on that bottom line. So everything that goes on the line above it, which represents the reactants that are used in this enthalpy change of formation, need to be balanced to represent 1 mole of the KBr at the bottom, which is why I've got a half in front of the Br2, liquid. Also make sure that those state symbols are correct. The arrow going up immediately from this line is my alternative route now, all the way around to the bottom line, so across the top, and it's going to be my enthalpy of atomization. And actually what I'm going to do is the enthalpy of atomization of the potassium first. I do typically do the metal first with these, but it doesn't matter which one you do. You can see here that I've turned the K from solid to gas, and I've done nothing to the bromine, just leave it alone. Do 1 bit at a time with these cycles. The next arrow up is going to be another enthalpy of atomization, but this time I'm going to look at the bromine. Now for the bromine, the enthalpy of atomization is the same as it is for the potassium. I need to make 1 mole of gaseous atoms. You just have to be careful that your formulae are done properly for all of the non-metals in these, as it's very easy to make a mistake. From this line then, I'm going to go all the way up to the top and do my ionization energy. But let's just have a quick label of everything that we've done so far and look at the individual enthalpy changes to sum up our process to this point. For example, here you can see that in the green, what I'm labelling up is the enthalpy changes of atomization and their equations, just to show you what these changes that I've done represent in actual written equation form. You must also be very careful to make sure that you include the state symbols in any of these enthalpy changes, because they're very fussy in mark schemes. This next enthalpy change is the minimum amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So that's right, it's the ionization energy. Now this only applies to the metal because it becomes the cation in the ionic lattice structure. So I don't need to show that anything's happened to the bromine. Think of the bromine as in your basket, but you're not doing anything to it yet. It's not going through the checkout. You've got to mention it on each line as you go around. Each line shows you what's in your basket at each point, and that's a nice way to think about it. My next enthalpy change is going to be electron affinity. Now it's the first electron affinity, there isn't a second in this diagram, but electron affinity is when you add 1 mole of electrons to 1 mole of atoms to form 1 mole of negative ions. All in the gas state, and it's what happens to the non-metals in these Born Haber cycles. You can see therefore I've formed 1 mole of the Br- and the electron has now been removed. My final enthalpy change is the lattice enthalpy. Now that's forming 1 mole of an ionic substance from its gaseous ions. And we can see here the Br- and the K+ are colliding together in a big exothermic enthalpy change right down to the bottom line. What I'm now drawing your attention to with the highlighter is showing you what changes from each line to the next. So remember that each line represents everything in our basket, but we don't always change something from one line to the next. It has to wait its turn. Also, in the video description, if you want to take a look at this now, I've also explained why some of these enthalpy changes will always have upwards arrows, which represents an endothermic enthalpy change, and why some of them will always have downwards arrows, which represents an exothermic enthalpy change. So be sure to check that out. This next example of a Born Haber cycle is for sodium oxide. It's a good example to look at because it uses a second electron affinity because the non-metal is in group 6, that's our oxygen. Same as last time, I put the solid ionic lattice on the bottom line. That's always our bottom line for these Born Haber cycles. And then I've got my enthalpy of formation going towards this, making sure that I balance all the elements in their standard states with standard formulae on that line to make sure that I have 1 mole of the ionic lattice at the bottom. This is our enthalpy of formation enthalpy change, and so I've got to make sure that everything balances to represent that definition very carefully. Same as last time now, but in a different order, I'm going to look at the atomizations. The atomization enthalpies are for the formation of 1 mole of gaseous atoms from an element in its standard state. So the enthalpy change, the numerical value, only matches up to when I have 1 mole of gaseous atoms being formed. So for the oxygen here, that's not too bad. I go from half an O2 gas to O gas atoms. But for the sodium, because of the formula of the lattice, if I was to actually do a calculation using the enthalpy of atomization of sodium, appropriate to this particular cycle, I would need to make sure that I multiply the enthalpy of atomization for the sodium by 2. Because the enthalpy of atomization only represents the formation of 1 mole of the gaseous sodium atoms, and actually for this cycle, I'm going to have 2 moles of sodium gaseous atoms being formed. That's why you can see I'm mentioning the ×2 on here. It's for any calculation you would need to do associated to this enthalpy cycle. The same is true then for the ionization energy. The ionization energy, remember, is for the formation of 1 mole of gaseous ions. Now here I'm forming 2 moles of sodium gaseous ions, and I've also got 2 electrons being shown on the top line right now. I would need to make sure in any calculations associated to this Born Haber cycle that I make sure to double the value here for the ionization of the sodium. My general tip for you for this, because it can be a little bit confusing, is if you've ever got a 2 in front of something on a line, then you need to make sure that you're checking to see if the value needs to be multiplied by 2 for the enthalpy change when that particular component changes at all. The next bit we're going to look at here is the first electron affinity of the oxygen. We use one of the electrons and we add this onto the oxygen atom that was on the top line. The other electron hasn't gone anywhere yet. We need to do a separate enthalpy change for adding on this second electron to the oxygen, and that's called the second electron affinity. Now you'll notice the second electron affinity is actually an upwards arrow, meaning it's an endothermic enthalpy change. You're going to have to check the video description for a bit of an explanation for that, if you're curious. That means, same as the last diagram, but a slightly longer way to it, the top line here has got all our gaseous ions ready and raring to go to drop down the right hand side in a big exothermic lattice enthalpy, taking us to our ionic lattice on our bottom line. Again, same as last time here, I'm just going to highlight what happens from each line to the next. Remember that we need to show everything in our system on each line, but only one thing will actually change from each line to the next. It's about being really careful with state symbols and awareness of your enthalpy changes for what you need to do from each line to the next. I really hope you found this video useful. Make sure you subscribe to our channel to stay up to date with all the videos that we're posting towards your exam season. Until next time, happy revising!